So I guess we'll officially kick off our kitchen chemistry session. This is one of another session of our virtual MagLab open house. We're sorry we can't be here in person, but you know, the benefit is you get to do this cool kind of thing at your own house, making, you know, something that you can snack on in your own time, right? So we appreciate all of you who have joined us here this evening, and we're gonna have some fun. Let's take it away. With our session.
Okay, thank you so much. I'm really happy to be here. I am a chemist, so I think that chemistry is everywhere. And our houses, we have the best chemistry lab, which is the kitchen. So molecular gastronomy is a whole new concept and is when food meets science. And the reason is because when we cook, we transform the food at the molecular level. So I have a question for the audience. Can someone tell me why when we boil eggs, it transforms from this liquid consistency to this hard, solid consistency?
Anybody know the answer? Why when we hard boil eggs do they change their structure? Put it in the chat. And Martha, while they're answering that question, just remind our attendees, what ingredients will they be working with tonight? We had a question from someone who just arrived, so they can go to the fridge.
So we need any vinegar. We need oil. So here I have cooking oil. We need eggs. We need the best emulsifier that you can find is the Dijon mustard. So here I have like grained Dijon mustard. And if you have lemon juice, it will be good. Also, if you have some salt, I like to use the pink salt. It will be good for making the mayonnaise.
Excellent. We have a couple of answers that the eggs change consistency. Does it denature the proteins? That's a guess.
Wow.
Because they're boiled in water.
That's great, and actually that's the answer. So when these are the like a representation of the protein structure of eggs, and when we boil it, they lose that structure. And then when it heats, and then it cools down, you ended up with this solid structure. So different molecular structures have different properties. These kind of molecules, they are liquid, they can flow really freely. But when you have this kind of molecules, they can interact with each other and they can form this solid consistency, right? So, and I have another question. Have you ever baked a cake in the oven? So if so, congratulations, because you are a scientist. So baking chemistry is all about chemical reactions. So for instance, here we have a muffin in which we have all the ingredients. So we have the flour, we have the gluten, proteins, egg, the butter, and the baking powder. But when you don't add the butter, so you don't provide a chemical compound that is critical for the gluten particles to stick together. So it's going to grow up. And then if you don't add the egg, you cannot provide enough material to build these.
Martha, you need to share the screen, please. We're not seeing your screen right now.
No?
Nope, we see you.
Oh, this is weird.
I wonder if I did something. Try it again.
Okay.
Oh, there it goes.
Oh,
there we are. Perfect.
That's interesting. So, okay. Okay.
Now we're good.
Yes. So again, so have you ever baked a cake? If so, congratulations, because you are a scientist. So baking chemistry is all about chemical reactions. For instance, here we have a muffin in which we have all the ingredients. So we have the flour that has the gluten, we have sugar, we have butter, which is the fat, eggs that provide protein, and the baking soda or baking powder. So when you don't add the butter, you don't provide a really important chemical compound that is critical to hold together the gluten particles. So the muffin will grow, but it won't be soft and fluffy. When you don't add eggs, the thing is that it's not gonna grow and it's gonna be so hard. And when you don't add baking powder, you ended up with this product that doesn't look really nice. And what's the reason behind? Well, when you have baking powder, you start producing a chemical reaction. Baking soda or baking powder has this compound that when it interacts with water, it will produce carbonic acid. And then eventually it will release CO2. And CO2 is a gas that is gonna fill all these air pockets. So when we have lots of baking powder, you will end up with these cavities or these holes that gives all the products like a fluffy consistency. So there are many ways to manipulate the food molecules to make really fun recipes. So we have three main techniques known as emulsification, spherification, and jellification. We have many others, but today we're gonna focus on these three. So let's start with emulsification. Here I have this container. So it's filled with oil and water. Can you see it? Yes. So, and no matter how hard I can shake it, if I start shaking it, you will see that eventually both phases will separate. So the process is actually really quick. Here we have the water, here we have the oil, and no matter how hard we try to mix them, it's gonna be separated. And the reason is because oil is nonpolar and water is polar. It has lots of oxygen atoms. So in order to bring these two ingredients together and that the mixture lasts over many days, even years, we need a special molecule known as emulsifier. So an emulsifier has two main components. It has a polar head, which is gonna stay with water, fruit juices, vinegar, and it has a non-polar tail, which is gonna stay with oil and in air for making fun preparations such as foam. We will see it. So here I have just an example. We have water, and you can see how the red heads or the the polar tails, sorry, the polar heads is gonna remain within the water. On the other hand, the non-polar tail is going to remain with oil, and that's how it's going to prepare or stabilize the emulsion. Because an emulsion is a mixture, and a stable mixture of both phases. So we have natural emulsifiers that we can use for making fun recipes. For instance, honey, because it has lots of sugar. So sugared molecules, they can act as emulsifiers because they have carbon, they have oxygen, so they can interact with both oil and water. The different kind of mustard, so Dijon mustard is so far the best. And egg yolk and lecithin, they have this particular molecule, which is known as lecithin, is the soy lecithin and egg lecithin, and it has two non-polar tails and one polar head. So here I have this container is filled with lecithin powder. So it's very useful for making different recipes. So for instance, we can make foams, and the way we do it is that we mix lecithin with the juice that we want to create a foam, and then we introduce air bubbles. So we're gonna see how we can do it. But if you want to do coffee foam instead of carrot foam, you can do it. So just brew some coffee and add some lecithin and introduce some air bubbles using an immersion blender. Or instead, you can use coconut milk and you can make coconut foam. Or if you want to make mayonnaise without using eggs, so you ended up with vegan mayonnaise, you can use soy lecithin, or you can make olive oil butter, or you can make other preparations such as red pepper raspberry emulsions. So let's see how actually we can make foams. The way we can do it is by using an immersion blender, mix the juice and the lecithin, and air bubbles will be introduced in the juice. So we will create a foam that can last for hours, even for many days. You will believe that just by using an immersion blender, which I have over here, and introduce air bubbles within the juice. It doesn't have anything to do with the emulsifier, that you can make that without the emulsifier. Actually, you can, but it only lasts like 1 minute or 30 seconds. But when you do it using the soy lecithin, it can last over several hours, even days. So this is how we can make molecular foams.
There's a question in the chat, Martha. If they don't have an emulsion blender, is there a way to make a foam without that kind of special device?
Yes, they can do it, but it's a little bit difficult. Okay. So they can do it with a regular blender, but it's a little bit difficult. So it will take lots of work to try to introduce the air bubbles, but for sure they can do it.
So if you're dreaming of your future foam making, it may be worth investing in an emulsion blender, it sounds like.
I'm wondering if a coffee frother might work, because that's very similar.
A coffee frother, that's a good thought. Maybe test it out.
I will test it out and report back.
So, and that foam can last like, I have made some experiments and it have last like 1 week.
Wow, a week?
Yes.
Like it'll stay foamy for a week.
Yes. Wow. So you will think that you can do it without the soy lecithin, but when you do the experiment, you see that it disappears right away.
That's
the secret to the bubbles. Now I know.
This carrot foam has me thinking of a fancy Easter side dish.
Yes, some students from the externship program, they did like nice recipes for the Thanksgiving dinner. Yes.
What did they make into foam? Did they have stuffing foam? Because stuffing is kind of foamy to begin with.
And they also use jellification for making some like desserts.
Oh, so cool.
So that's the way you can do it. I have used different ingredients. Like I started with carrot, but then I went with coffee, coconut. I made all those examples. So soy lecithin is a really good natural emulsifier that can replace eggs. So if somebody is allergic to eggs, so it's a good option. Okay, so now, what about salad dressings or what they call vinaigrettes? The question is, it's just about vinegar, oil, and spices? Okay, so first, let's go a little bit on molecular composition. So vinegar is the mixture of acetic acid and water. Both molecules, this is water molecule, it has 1 oxygen atom, 2 hydrogen atoms, is very polar. The acetic acid is this molecule and it has 2 oxygen atoms, so it's really polar. On the other hand, oil is a non-polar molecule. It has, or it is a hydrocarbon chain. It has carbon, hydrogens, and is non-polar. It doesn't like to interact with water. So this is what you can find in the grocery store. You will usually see phase separation. This is a salad dressing that you can buy. And you can see how the oil is separating from the vinegar or the water. So in order to prevent phase separation, we can add a natural emulsifier. And for vinaigrettes, the best one is the Dijon mustard, because it has these kind of molecules that have lots of oxygen atoms on it, so they can interact with water, and it has also carbon and hydrogen, so it will interact with oil. So now the question is, like in a chemical reaction, do you think that the amount of the ingredients matter in chemistry kitchen, in the kitchen process? Do you think? It's like, I don't know, like in a chemical reaction, if I add vinegar and oil, and mustard is like the catalyzer of the mixing reaction to create a stable emulsion, do you think that if I have, for instance, 3 parts of vinegar that I have over here, and only 1 part of oil, it will create the same emulsion as when compared when I have 3 parts of oil and only 1 part of vinegar? So the result is different. So if I add different amounts of the emulsifier, which is the Dijon mustard over here, you will have a different result. So for instance, let's try with this one, which is gonna create the most stable emulsion because the oil is gonna, or the vinegar is gonna disperse into the oil. And in this one, it's gonna be the opposite, but it's not that stable. So let's try to make the emulsion. I will introduce our emulsifier, which is the Dijon mustard, into the containers.
Martha, can I stop your screen share so we can see you better?
Yes.
Thank you. There we go.
So I have it over here, and then I'm gonna shake. And you see how it got really thick. And now I have 3 parts of vinegar and only 1 part of oil. And I'm gonna add the Dijon mustard.
Martha, should everybody be following along, or is this just a demonstration?
This is a demo, but they can do it, so I can wait for them.
Okay, but there's more kitchen chemistry coming up, right?
Yes, so we're gonna make the mayonnaise.
Okay, so we'll keep this as a demo.
But you can also make this if you have this stuff at home. It's just oil and vinegar and Dijon mustard, right, Martha?
Yes, so here you can tell the difference. You can tell how this one is separating really fast. It flows, but this one got really thick, and it's gonna be stable almost for, like, this one is almost a year.
Wow.
So I have this one that, yes, that I made a year ago, and it's still stable. I have a little bit of free vinegar in the bottom, but it's really stable.
So Martha, remind us, just hold those 2 up again for us one more time, and remind us which one has which mix of ingredients, right? Just hold maybe both of them up one more time. Yeah,
Yes,
and
so,
like which one is that?
So this one is 3 parts of oil and only 1 part of vinegar. And it has just a tiny amount of Dijon mustard. And this one, you can see how it's separating really quick. Like here I can see both faces. Oh, you can see it. And it's 3 parts of vinegar and only 1 part of oil. So this one, this is the right.
Did everybody get that? So I'm just making sure everybody got that. So the one is the 3 parts oil, 1 part vinegar, just a teensy bit of Dijon mustard. The other one is the opposite, 3 parts vinegar, 1 part oil, teensy amount of Dijon mustard. Is one of them right and one of them wrong, Martha, or is it to taste?
This one is right. This one is wrong because you can see how we have how we have phase separation. So it's not going to be stable. Like it's already separating. But this one, it can last for almost a year. So this emulsion over here was prepared last summer, I think, and it's still stable. So as in chemical reactions, we can conclude that the amount of ingredients matter. So the amount of ingredients are important for cooking. Okay. So does anybody in the audience has any question, or they did the experiment, or they want us to wait for them?
I have a question. So you showed us the one that you made a year ago. Does temperature matter in keeping it stable? Does it need to be refrigerated to stay stable?
This one wasn't refrigerated, but temperature is a critical parameter for emulsion stability. So there are some emulsions that, depending on the ingredients, or like for instance, petroleum emulsions, or in the cosmetic industry, that they require a particular temperature conditions. So it depends.
Thank you.
But these ones, they remain at room temperature, like 25 Celsius degrees. Okay, so do we have
after our audience makes after our audience makes this vinaigrette, should they keep it in the fridge then, or can they just keep it on the counter? Is that what did you answer?
If it's for actually like eating, they should keep it in the fridge because of the Dijon mustard and the water content of the vinegar. Like, it can cause some side reactions that we don't want.
Okay.
Okay, so
no, this is not the experiment that you got. Just to clarify a question in the chat, this is not the experiment that you got, the ingredients we talked about at the beginning. This is like a bonus experiment. And if you know, it's pretty simple. It's just oil and vinegar and a little bit of mustard, and it's something else you can just whip up, right? Just 3 parts. Yeah, so it's that 3 parts oil, 1 part vinegar with just a little bit of Dijon mustard for your own custom vinaigrette, if you so choose. And if you want, you could just make that later.
It's freebie science.
Yeah, freebie lessons.
Okay, and here is just the recipe for a bittersweet salad dressing, in which we mix 30 milliliters of lemon juice, 1 teaspoon of whole grain Dijon mustard, which is the perfect emulsifier, is this one for lemon juice, olive oil or avocado oil, because those are really healthy, and honey. So, and when you mix it, you will have this kind of consistency. And honey and whole grain Dijon mustard will make possible that the emulsion lasts for almost 2 days. So that's just a recipe that you can make at home. And then now we're gonna make the recipe for the ingredients that were listed at the beginning of the presentation, which is for the mayonnaise. So for making mayonnaise, the typical ingredient or emulsifier that we use is lecithin from the egg yolk. So keep in mind that it has this molecular structure. So it has 2 nonpolar tails that will be interacting with the oil. I'm gonna use this cooking oil, which is canola oil. But you can use avocado oil, olive oil, any other oil, and it will be possible to make the mayonnaise. And it has this polar head, which has nitrogen and oxygen functionalities. And it will interact with the egg proteins and the lemon juice. So this is my reaction flask. I will stop sharing.
I got you.
Okay, so now you can, okay. So this is my reaction flask. These are all my ingredients. So I have the lemon juice. Oh, can you see it? Oh, lemon juice. I have the cooking oil. I have the egg yolk, and I will use a little bit of Dijon mustard. So I will add the ingredients.
Hey, Martha, about how much oil is that?
Is 200 milliliters, around 200, yes.
Okay, 200 milliliters of oil. About how much are we putting in? What's this?
So 200 milliliters.
Okay.
And the next is the egg.
The egg is a whole egg. It has to be at room temperature, because if it's cold, it's not gonna work.
Ah, okay. That's a key part of that. Room temperature egg.
Then the lemon juice.
About how much lemon juice would you say that is?
It was about 20 milliliters. So it was just a small lemon.
Juice of 1 lemon. This is a good time to remind everyone that when we do science, we use SI units. So we don't use cups and teaspoons and tablespoons.
Yes. And this is just a little bit of Dijon mustard. So it's gonna help for the emulsifying process.
Just a pinch.
Yes. And usually salt is going to improve the emulsification process because ions are also important for making emulsions.
Got all the science I'm learning.
And then the emulsion blender. So please, I don't want to make a spill on my computer. So, and you see how it's changing. And you can see how it got really thick. So we got a really stable emulsion, which is the mayonnaise. So it has a different appearance. It's really thick. It actually looks like kind of white, yellowish, because it's an emulsion. An emulsion has they have different properties compared to the initial ingredients. So how is the audience doing? Could they do it?
All right, everybody, if you did this, let us know how your emulsion is coming along, how your mayonnaise is going. And while you're working on your mayonnaise, I want to remind everyone that this is where chefs get to be a little creative, because Martha and I did this activity during our summer exploration series. And one of the students said, well, I only have Japanese mayonnaise. And we're like, let's go, let's do this. And so you get to add different things to spice it up and change the flavors up a little bit. Like you mentioned, avocado oil instead of olive oil.
Or if you are vegetarian, instead of using eggs, you can use a higher amount of Dijon mustard, or even the grain Dijon mustard, the one that I showed for the previous recipe. That one is much better for making those kind of recipes.
And at this point, you can throw in all these spices and everything. Like if you wanted to spice it up, you put a little cayenne in there.
Yes.
Ooh.
And usually
sriracha mayonnaise. You can add sriracha.
Yes. And those ingredients, they have molecules that they contribute for emulsion stability. So that's also good.
Awesome. So we have some people who are trying. We have some people who are trying at home. Anybody need any help? If there's something you're struggling with, go ahead and add it into the chat. Martha, if they don't have that immersion blender at home, can they just do it with the traditional blender on, is there a special setting do you think that would work the best, or by hand?
Yes, so they can do it with the traditional blender. So what I recommend to do is just first add the egg, the lemon juice, all the ingredients, and just when you turn on the blender, add drop wise the oil. So when you do that, you're gonna create the most stable emulsion.
Okay, so you hear that? If you're using a traditional blender, you put in the oil last, right? That's what you're saying, Martha. Put it in last, kind of as you're starting to blend.
Yes.
Great tip. Great tip. Anybody else struggling with anything at home, either from trying to make this mayonnaise, or maybe you're still making a vinaigrette from the lesson before? I don't know.
And we can see it here. The one that have 3 parts of vinegar is already separating. But this is the one that we prepared today and is very stable. So perhaps I had to mix a little bit harder, but if you do it, you can actually have this consistency that lasts over a year.
I'm amazed by that time frame, that an entire year. I was really thinking weeks, maybe months, but not a whole year. So that's exciting. All right, no reports yet. No one else has chimed in to let us know how their emulsions are going. But I know they're trying. A couple people have told us that they're trying, so hopefully we have results soon. Okay, were there any more slides that you wanted to show?
Yes. So let's go back to the presentation. Okay, so here is the recipe for the mayonnaise that we just made. And I just want to say that emulsions are central in the food industry. So for instance, cream, butter, milk, those are emulsions. Ice cream is an emulsion. And not only in the food industry, in the cosmetic industry, we find it everywhere, like in the shampoo, body lotion, face serums. And also, we care about emulsions because of oil spills. And oil spills are critical for the environment. For instance, the Deepwater Horizon oil spill that happened in 2010, its spill was over hundreds of millions, I think hundreds of millions of barrels in the Gulf of Mexico. And it's really critical for human health and the environment. And the reason we care at the MagLab about oil spills is because we use our powerful magnets in order to understand the molecular composition of petroleum molecules as they are released in the sea. Okay, so let's go back a little bit to molecular gastronomy. We have two additional techniques. One is spherification, and the last one is going to be jellification. So in spherification, we can make caviar, and we can make caviar using every liquid that we want to use. For instance, with asparagus juice, we just make caviar, or balsamic vinegar, or fruits, coffee, kombucha, honey. And how we can do it that? So we're going to trap fruit juice or whatever liquid you wanna do it inside a sphere. And this sphere consists of a gel that is created by sodium alginate, which is a gelling agent, is natural. And we are gonna create the gel when it's mixed with calcium ions because they coordinate in this way. So these are the alginate molecules and they have lots of oxygen on it. And they like to coordinate with calcium ions. So when they do this chemical reaction, they produce like a wall that is gonna create the sphere. So like in this example, this is cranberry juice, and we just created the spheres by using this chemical reaction, and it's completely safe to eat it. And the way we do it is we have the juice that we want to transform in the caviar. We dissolve the alginate, the sodium alginate in that juice. We let the air bubbles to escape the solutions. In a separate bowl, we are going to prepare the calcium bath, and then we are gonna drip this solution, the solution of the juice and the alginate on the calcium bath. And then we're gonna create the spheres, and we need to rinse them. So we will have like stable caviar. So here you can see the process.
I love the colors too. It's so, I mean, the spheres are very cool, but the colors are just delicious.
So there are some juice that they have naturally calcium, and the process won't work on those ingredients, but you can solve that problem if you use vitamin C, because it will capture those calcium ions, and then you can use, you can do the process. So that's a common problem that people usually find when they try to start doing the caviar.
If you've ever tasted a fruit caviar like this, let us know in the chat where what you tasted. This is so cool. Martha, you've tried this with several things before.
Yes.
Which things do you think work the best in this particular kind of gastronomy?
I really like cranberry. It works really well. And it has high vitamin C. So if it has some calcium in it, we won't have any trouble. But the key part of the process is that you let the air bubbles escape the solution of juice and alginate. If you don't do that, you won't get the caviar.
Okay, I'm gonna say it. They just look cute. They just do.
Yeah, that's really cool.
And you can do the process with the caviar maker. And in our open house in 2018, we did it with the caviar making.
And hopefully coming back to a future in-person open house again. Stay tuned.
Oh, I know what I'm getting off Amazon tonight.
So you can find those ingredients like in Amazon, also Mother Pantry, I think, is another company that they sell the molecular gastronomy ingredients. Okay, that was direct spherification, but there is another technique called reverse spherification. And in this case, the liquid that we want to create the sphere, we are not going to mix that with the alginate. So we're going to do the opposite. We're going to mix that with the calcium ions. And then the bath is going to contain the alginate. And this technique is powerful because it allows us to create bigger spheres. And it's usually used for making yogurt ravioli. So let's see how you can do it. So the alginate is the bath. It's going to be mixed with water. So the immersion blender is really useful for many recipes in molecular gastronomy. Then the yogurt is going to contain the calcium ions. So that's the calcium salt, which is known as calcium lactate. That's why we in molecular gastronomy, they write it as Cl.
They look like little pearl onions.
I was going to say they were like little tadpoles and would be great for Halloween.
So weird.
So they
That's
burn
just so-
really easy.
So when you eat this, it's sort of like gushes, Martha. Is that that's the game? Like it almost like pops.
Yes.
Ooh, so fun.
Yes.
Martha, I had to ask you a question about the foam. I know that was a while ago, but when you eat it, I kind of picture it being like cotton candy, like where it almost dissolves.
Yes.
Is that kind of what it's like, or does it have more of a consistency?
No, it's really similar to that one. Yes.
Okay, cool.
Okay, so and then we're gonna look our last sorry about that. Our last recipe or technique, which is jellification. And for doing jellification, we can use agar. So similar as when you boil eggs, agar, it has this molecular structure that when you heat it, is gonna create those kind of strains or like chains. And then when it cools down, it's gonna trap some liquid on it and it's gonna create the gel. And you can create noodles from everything, I think. So this, for instance, was, I think that broccoli noodles. So let's see how you can create chocolate spaghetti. Let's see.
Two of my favorite things, chocolate and spaghetti. This is my dream, Martha. You're making my dreams come true.
Okay.
And maybe you could get your kids to eat carrots if it tasted like carrot cotton candy, right, Carlos? That might be a trick.
Yes.
for that foam.
With my son, I may have to resort to that.
So that's the magic ingredient, which is agar-agar. So, and the reason why water is critical in this preparation is because the agar-agar molecules are gonna trap water molecules, and that's the way you create gels. So then dark chocolate. This is just for to give some extra flavor on it. And the heat is going to activate the agar-agar molecule. So if you don't apply heat, you're not going to have that effect, because it's really similar to the boiling process of the egg. So you change the molecular structure with heat. So you have over here a container with ice. And then you just feel like the tubing. We use food grade silicone tubing for that. And then you let it cool down for over 1 minute. And that's the way you can make the noodles. You can use a really long tubing so you can make many at the time.
Wow, that's so fun. What kind of sauce would you put on chocolate spaghetti, though? That's the question. I'm just kidding.
Cherry sauce, some cherries or strawberries.
Strawberry sauce on chocolate spaghetti. Now that sounds good.
Yes, this one is a really nice presentation. So those are the main techniques, emulsification, jellification, and spherification that chefs usually use for molecular gastronomy. So there are many others, but those are the main three ones. And this is all.
Awesome. So do you have questions for Martha about, things you cook and the chemistry behind them, or anything that you saw tonight, how to make something that we talked about tonight? If you have questions, this is your chance to talk to a chemist and a molecular gastronomy, interested person, right? To kind of try all these quirky things that you have always wondered about. Martha, I wondered, when you were trying to do this kind of work before, there has to be a learning curve, right? So can you share a story about maybe your biggest kitchen fail, even as a chemist?
Oh, it was, for sure, it was the caviar. So I tried over 10 times the caviar and it was impossible. So the first fail, it was about the air bubbles. So because I had a lot of air bubbles in the solution of juice and alginate, when I was dropping the solution in the calcium bath, they will float and they won't go to the bottom. So they won't create the spurification reaction. The other issue was trying to make the process with juices or liquids that have a high calcium content. Like the orange juice you can find at the grocery store because they add calcium on it. So I had to learn that you can use actually more vitamin C in order to capture those calcium ions, and then you can make the process. So for the chocolate spaghetti, so usually because I want to eat it so fast, I won't wait for 1 minute. You need to wait over 1 minute until it cools down and it creates that jelly consistency.
Okay, that's always a fail in my kitchen, is waiting long enough for the food to be actually ready. I always feel that way. There's a question in the chat about whether, particularly for our local audience, do you know of a restaurant in the community of the National MagLab here in the Tallahassee community that uses any of these processes in their own recipe menu?
Actually, I was thinking about like a business opportunity. There is one in Chicago. there is one really famous restaurant in Spain, and for having the opportunity of sitting there and eating, you need to wait over 1 year before the pandemic. So
wow, like it's a 1-year wait list to get a reservation. Oh my goodness.
yeah, so in
Wow. So
Chicago,
anyone who's been
it's more accessible. So it's just
okay,
like
I was going to say anyone who was inspired by these techniques tonight, you might want to come to tomorrow's session at 1 p.m. on STEM entrepreneurship. It sounds like there's an opportunity to marry some STEM concepts with a restaurant here.
Well, I hate to burst some bubbles. They're not going to be first because Sidecar Gastropub in Tallahassee is doing similar things that I can see. So
okay, so those of you looking to taste this, you could try Sidecar. Apparently, they do some cool, quirky kitchen chemistry in their recipe. Martha, if you could only eat one food for the rest of your life, what would it be?
from one of the techniques, I would like to eat caviar, because I can make fake caviar from everything. So I can eat like vegetable caviar, the fruit juice caviar, beer caviar. I have also made caviar with beer, so it's good.
I second the caviar. I'm all for that.
Oh, Carlos, there's a comment that Sidecar closed.
Oh, well, how about that? Then there is a business opportunity there for everybody. Join us tomorrow with Jeff Whalen for Entrepreneurship in STEM.
Yeah, that's going to be a great conversation about STEM entrepreneurship. And it sounds like there really are opportunities.
Yes, I think that in the audience, we have one of the students of the externship program, Alexis Manners. And she was able to make a challenge, and it was making a ravioli that could disappear in your mouth, combining different techniques. So it was jellification. It has also spherification because the ravioli was filled with special ingredients, and it was also another kind of jellification with xanthan gum. So she was able to make that recipe that only like really skilled chefs can do it. So she did it.
Wow. Bravo, and bon appetit, because that sounds fantastic and absolutely super, super cool. Maybe we can talk someone into this idea tomorrow, Carlos. We're definitely going to bring it up.
If anybody can make it happen, Jeff Whalen is a person that can make it happen. So
yeah, we know it, and we clearly need to partner someone here with Martha so that they can learn the complex chemistry behind this. So Martha, how did you get into this molecular gastronomy? I mean, I know you're a chemist by trade, and you know that there's a lot of comparisons, right, between chemistry and cooking, but like, how did you this is so cool.
So one day I was watching television and I saw a documentary about El Bulli, which is the most famous restaurant, and they were the first ones who were trying molecular gastronomy techniques. And I saw a documentary about the chef and the restaurant and how you have to wait over a year for the waiting list. And I just got really interested. It's really nice because it's pure chemistry. Usually when people cook, they don't think about chemistry, but as we can see it, like it's about chemical reactions. Like you can see it over here, like this combination didn't produce a stable emulsion, but this one is stable and it's gonna last for over a year.
Do you think being a chemist makes you a better cook just in general? I mean, these are some fancy techniques that you shared tonight, and clearly they take, some special knowledge, but just in general, like if you're just whipping up a dinner, do you think having that chemistry foundation just makes you, a better cook?
No, I think that what you need is curiosity. I think that what you need is to be interested in reading, in watching YouTube videos, because there are many YouTube videos that in which people explain a lot. So I think that I have friends who are not chemists and they can cook much better than I do it. So
that's a great explanation. Curiosity, a key ingredient for so many things, right? Science, cooking, all sorts of things. Take a big dollop of curiosity to fuel them. Carlos, you have any more questions?
I got one. I do got one. Martha, you're from Colombia, correct?
Yes.
So what food from Colombia that you can't find here do you want to use to make your caviar?
Is an special food that is made with shrimp. So it's like a soup, but it's so delicious. I haven't been to Colombia for almost 5 years, and I think it's gonna be the first dinner I'm gonna have. So it's called cazuela. I don't know if there is a translation for that word. And I would like to make caviar with that one and noodles. So last weekend I was trying a recipe for doing miso soup in noodles. So you can make it. So I will try to make it.
That sounds amazing.
That does sound amazing. I'm all for that.
That sounds so delicious. Martha, do you have any secrets of the kitchen? Like are there secret chemistry involved in any recipes that you know of that you want to spoil for us today as an audience? I'm just curious if you have any insights.
Yes. So Starbucks coffee is real nice. I love going to Starbucks and having the frappuccinos and having the other preparations, just a regular coffee. And what they use for most of the preparations in order to have that consistency, like that body, that flavor, is just using a pinch of xanthan gum. So if you just brew regular coffee, you can put it on the blender and just add a pinch and you will know the difference. It's gonna be so delicious. So
Wow.
yes, that's one of the main secrets, and that costs millions of dollars.
Wow, you heard it here, guys. Try some xanthan gum in your coffee and see if it changes things. It sounds like that is a good tip to get here. There's actually a great question in the chat about whether you've ever studied food at the MagLab. I know you study
No.
all sorts of things, but have you ever studied food?
No, with mass spectrometry, here at the MagLab, we haven't done that, at least myself. I will ask my colleagues, but I know about a case, and it's really interesting. So in one of the conferences, I met a professor from the University of California, and he was trying to understand the composition, the ideal composition of the milk for babies in order to make formula. So he will study which babies are healthy, and he will study the genetics and all the composition of the milk that those babies were given. And then he will try to formulate like the real formula for selling that formulation.
So cool.
Yes, that is one cool application. Another
Kirsten,
application was making chocolate bars with 100% chocolate, all the products from cocoa, and they were sweet. So that's another project that is working out well in Colombia. But
That's so
everything
cool.
is chocolate, so it doesn't have any like glucose, like sugaric or additional ingredients. Like everything is from cocoa, and you can taste it like really sweet, and it's gonna have a lot of fiber, so it's gonna be very healthy.
That is fascinating. And Martha, I think about the ion cyclotron resonance technique that we do at the MagLab that you do as a real scientist. I just want everyone to appreciate, we're just hanging out here with Martha, but she's a fancy chemist at the MagLab. And today she's talking about food and stuff, but she's making like really important discoveries about the world. And it's funny because I think about that complicated instrumentation as almost giving researchers like the ingredient list of really complicated chemicals, right? Or things that are very chemically complex. So it's funny to me to make this comparison with kitchen chemistry, because I think about ion cyclotron resonance as sort of providing, for something like oil, for example, which I know you've studied yourself, complex petroleum samples. And the ICR instrument really spits out sort of the chemical components in a sample, which is sort of like having an ingredient list.
Yes, it has millions of different molecules. If you think about the complexity of the sample, think about a glass of water. it has millions of molecules, but all are the same. If it's pure water, everything is going to be the same kind of molecule. If you have a can of soda, you will have also millions of molecules, but perhaps you will find 10 or 15 different molecules, sugar, some flavor, the color. But then if you look at petroleum, a single drop can have millions of different molecules.
Wow.
And yes, we use our magnets to understand decomposition and tell the industry, the petroleum industry, how to do a better use of those resources and how to solve the spills.
Yeah, really important work, but it's so interesting to think about it as like the molecular ingredient list of like some of the most complicated chemistry things in the world, right? Some of the most chemistry intensive complex makeups in the world. So very, very interesting work that you do in your real job. Carlos, I think I interrupted you. You were going to say something.
I do have an answer. I can say that food has been studied at MagLab because we had some middle school mentorship students working with a scientist studying the free radicals of used coffee beans. So that is something that I know has happened. I'm sorry, Martha, what was that?
That's a really interesting application because it has to deal with our health. Yes. And also in the roasting process of the coffee, they can create some phenolic compounds that they can, I don't know, like fight against aging. So those are really like powerful.
Wow. Wow, if that doesn't sound remarkable. There's also exactly some research on turmeric that's happening. In fact, there's a great story about it in our most recent issue of Fields magazine. And I know there's a story about researchers using NMR magnets to learn about, I think it was sweet potatoes, but I can't remember the details, so I'm not going to be of much help here. But this is, but yeah, food is fascinating and such a great way to understand, some of the science behind what's happening at the MagLab. For example, in the ion cyclotron resonance facility, that high precision instrumentation that you use to get those very, very precise ingredient lists, which is the simple way that I describe it as a non-scientist.
Yes, and the turmeric project sounds really interesting because turmeric is one of the most powerful superfoods that people now are using for health issues. And just understanding the reason behind the molecular structure and why it does what it does is a whole project.
Yes, excellent point. All right, this is really your last call for questions. We are going to wrap up this session tonight. We know you guys have been cooking and prepping, and we've had so much fun talking about all these really cool methods of preparing food and the chemistry behind the experience. If you have any final questions, get them into the chat really quickly while we wrap it up here and say good night. And say, of course, thank you to our presenter for this excellent and delicious session. It's by far our tastiest session in this open house season. And we hope to be able to have everyone back at the MagLab sometime in the future, and maybe even see this happen in person at some future sessions that we might plan, right, guys?
Yes, I
Don't
hope
go away.
the Christmas dinner. So, and I will share some dishes based on molecular gastronomy.
Very, very exciting. So stay tuned for that.
Don't go away just yet. We're going to say goodbye, and then you're going to get a quick invitation for a survey. Give us some feedback. Let us know what we're doing right and where we need to improve, because we want to make open house better every year. So
exactly. Thank you to everyone who joined us tonight. We hope to see you at a future session.